Okay, so at a certain point, some parts of physics are very repetitive. I'm not going to say this is everything we do in physics, but a large portion of it is I'm going to give you a scenario. You're going to get some numbers. You're going to need to pick out what formula you should use. Once you figure out what formula is necessary, you need to properly put the numbers in the formula. Use your super awesome algebra skills because you have those. You're a really good math teacher. Thank you. And basically solve, right? And then don't miss little details like units or sig digs or directions. Right? And so today's lesson is really kind of more of the same. I'm just going to reintroduce you, remind you of some other formulas that hopefully you've done at some point. So, today's topic then is the formulas on work and energy. And so, fun cartoon to start with. Anybody else like this? Just busting at the seams, just ready to get out of here. All right, so let's talk about work. Work is defined as whenever you transfer energy. Work and energy are actually really challenging words for physicists to try to define. A lot of times we know what work is, just, like if I tell you a scenario, you go, yeah, no, that's work, right? If I push the stool, did I do some work? Yeah. It kind of makes intuitive sense that I accomplished something, I did something. Did I use some energy to do that? Yeah, that kind of makes sense. So a lot of times we intuitively can pick up and like it passes the smell test and you go, no, that's got to be work, right? But it's kind of hard to define it because sometimes we define work as transferring energy and sometimes we define energy as the ability to do work. Sometimes those are the definitions. Energy is the ability to do work and work is the ability to do energy, transfer energy. So here's maybe a better definition for work. It's more of the formula. Work is a force times a distance. If you apply some sort of force, do you guys know what a force is defined as? A couple of P words. Push or pull, yeah. A force is usually some sort of push or pull. If you push or pull something over a distance, that's work. So that's actually, I guess, was on my next slide. Good catch if you didn't see that beforehand. So. If you push or pull on something, and it moves, by the way, it has to move. That's a characteristic. Then that's work being done by a force. So, and that's all about energy transfer. So, work and energy are like super close related. One more thought. This doesn't really matter to us yet, but it will in one of our later units on dynamics. The direction of motion, like the force and the movement, they got to be parallel to each other. Are there any extras? Okay. All right. Sorry, I'm going to kind of rush through because I know it's Friday and we don't have quite as much time. So slow me down if this is going too fast. So, what is energy is a really challenging question because this is what I just mentioned here. Physicists know that energy is what we do to perform work. So like I mentioned the last couple minutes here, energy is defined as your ability to work. Work is energy, energy is work. They're kind of interrelated, essentially. So here's our first step. Here's our first formula. This one's not on probably your current data sheet, I don't think. Basically, if energy occurs, if there is some sort of change in energy, the reason why that energy was changed is something did some work. So essentially, if I tell you you did 5 joules of work, it means that you must have changed your energy by 5 joules. That makes sense. For those of you guys who did chemistry with me, maybe think of, remember how we did like thermodynamics and we did like potential energy diagrams where that would be your change in energy? Okay. Why did that energy take place? Well, some work occurred. That makes sense. So, long story short, energy is work. That's a really boring formula. This is more one that we'll do something with. If you want to calculate how much work was done, here's another way of doing it. Take your force times by your distance. So, okay, let's slow down a little bit here. So now I can finally get to nitty-gritty details we should focus on. Work is measured in one of 2 different units. One of the units is known as a Nm. That N is not a prefix. It's a Newton meter. So a Newton meter is how we can measure work. Or the other equivalency is called a joule, which is named after James Joule. Have you heard of some of the experiments he did? Any of you guys in my grade 10 class last year remember the experiment that Joule did? What was the experiment that he did to try to figure something out? Do you guys remember? He did, yeah. He had like a stirring thing, right? And what he ended up doing is he dropped a weight, and as the weight fell, it caused the stir to stir something, and that found how much temperature change there was. Talking about the story at some point. Anyways, in his honor, we've named the units for work after James Joule. Force is measured in newtons, so N is capital N. Thanks, Jessica. For Newton, named after Sir Isaac Newton, the guy with the apple falling on his head. And as always, a distance is measured in meters. One more thing that I should point out here. Individually, force is actually a vector because it has a direction. So even though I didn't do a very good job of it on here, individually, force is actually a vector. And I wrote distance, but you guys know that a distance can also include a direction as well, right? So if we just change the word out here for distance, we could put a little arrow hat on top of this as well and say that we could attach a direction to those as well. It has to be the same direction though. Whichever way the force is being applied, whichever way the direction it happens to be going, they have to be the same. Here's the weird thing though. Work is not a vector. There is no direction for work. Okay. Similarly to energy, we do it in a second here, there actually is no direction for those things. So although the product individually we can have a direction for, we won't for this one. Alright, let's try some examples. You did 64.7 joules of work. You lifted a heavy object at a distance of 5.73 meters. So that we can algebra this thing and find out how much force there was. I know this may be a little bit redundant to do this for such an easy question, but sometimes I might say, well, okay, I know my work value. I did 64.7 joules of it. I know that my distance that I traveled was 5.73 meters. We are looking for force. Find me a formula. There it is. What's the other unit for joules, though? What's the equivalency? Newton meters. And for unit purposes, you may find it easier to write this as 64.7 Newton meters rather than joules when you're writing work. You'll see why in a second when we cancel units. I don't know what my force is. I don't know my distance is 573 meters. Most of you guys are probably way ahead here, right? In order to solve this, divide by the 573. The reason why I recommended changing your unit type though, can you guys visually see how this meter and that meter will cancel? You'll get your answer in newtons. So, anybody have an answer? 11.3? Consensus? Awesome. Okay, on this particular question, I was a little lazy. I didn't actually give you any directions, but the force and the distance should have been going in the same direction, right? So if it was the force was going west and the work was going west, or the distance was going west. So do make sure that if we actually add some directions to this in a bit, that they're going the same way. So far, so good? Awesome. All right. You pushed with 85.6 newtons against an immovable object. How much work did you do? None. Good, yeah, I'm getting to some tricky questions here, right? I decide to go up against the board and I push against it. If it does not move, despite my using of force, it needs to actually move, right? Essentially what's happening is you've got work is equal to your 85.6 newtons times by 0 meters, so therefore you did no work. Alright, here I throw in a twist. You got a championship weightlifter. He uses 6,000 joules of energy to lift a barbell 180 centimeters. What's my twist? Yeah, can you handle the centimeters twist? So let's find the amount of force. Okay, well, actually, I threw one more twist in here. I said how much energy he expended. Well, work is equal to energy, right? Does that make sense? So either way, even though I called it energy, we use 6,000 Newton meters worth of work / energy, whichever one you want, right? The work he did was accomplished because he used his energy to do so, right? The distance traveled was 180 centimeters. You guys convert that into meters? What is the prefix for centi? 10 to the minus 2, yeah. So what you could do is take this centimeters and make it times 10 to the minus 2 meters if you want. That's a nice shortcut way to try to change it. Long story short, it's 1.80 meters. As long as you can handle that, right? You're dividing by 100. Okay, work equals force times distance, 6,000. I'm just going to skip a step here. You guys can probably handle this. Divided by 1.80 meters. Yeah. Cancel out the meters. Do you get an answer? What'd you get, Walker?
3,000.
Repeating? Anybody else? Okay, so if it's 3, 3, 3, 3 repeating, we just need to get the sig digs right. So 3 sig digs? So let's make it 3.33 times 10 to the 3. That's how many newtons we would have used. Let's throw one more thing on this answer. Which way did he move it? I think we can assume we can figure this out based on the question. Yeah, I think up makes the most sense, right? So that's the one thing I have been skipping here, is that if the distance was up, then the force must also have been up. Does that make sense? So even though I've been kind of a little bit lazy with some of the notation here, if we ever end up having two vectors multiplied actually gives you a scalar though. Work and energy actually have no direction. And I actually should talk about that now before I forget. There are lots of different kinds of energy, right? One type of energy could be the energy that happens with work, right? And so if I lift a barbell up, it does make sense there's a direction kind of for that, right? But there are other types of energy. For example, light energy. Which direction is that light going? It's kind of going everywhere, isn't it? I can't say that the light is going north or south or east or west in the same sort of way that I'm saying that the barbell is going up. Makes sense? Sound energy is another good example. I mean, granted, yes, my sound waves are traveling, but I mean, they're not just traveling one direction, right? They're traveling lots of different directions. So there are some types of energy where you might want to argue, well, if I throw a pin that way, there's a direction to it, right? But hopefully you'd agree, there's other types of energy where there really isn't a direction to it, right? Like nuclear energy. How could you assign a direction to that? Does that make sense? So because energy sometimes really can't have a logical direction, and energy is equivalent to work, even though it might seem like work should have a direction, we won't put a direction on work. Okay, that was a good segue. Let's talk about the different types of energy then. Essentially, there's two main categories. One is potential energy, and you guys know the other one without looking at the notes? Good, okay, yeah. So potential energy describes anything stored, right? I mentioned this earlier in class. If you've taken chemistry, right, the idea that if we draw a potential energy diagram, here there is a change in energy as energy is being released to the surroundings, right? Energy is stored inside bonds or stored inside whatever it's stored in, right? And as it's released, that energy just doesn't disappear, it causes work to be done of some type. Maybe the best example I could give is, imagine that you got a slingshot, right? And I pull back on the slingshot. Am I currently doing work once the slingshot is pulled all the way back? I had previously done work, In order to pull it back, I applied a force over a distance. But as I'm holding the slingshot right here, I'm actually doing work. Not anymore, right? I did the work to get it there, but now I'm just holding it, right? There's no more distance being applied. That potential energy is just waiting there, right? In a way, it's kind of like this graph here. There's a lot of potential energy just waiting there, right? And eventually that energy is going to get lost. I'm using my fingers, right? But it's not really going to get lost. What is that energy going to do? Well, it's going to do work on the slingshot object, and it's going to fling it across the room, right? And therefore it'll give that object energy, right? So energy will get transferred in some sort of form. So long story short, potential energy is something stored, and at some point it'll get released. Here it's being stored. There's a lot of energy in store. Here it's been released. And the difference in this energy is going to cause some sort of work to be done. Here's the main forms of potential energy. One of the biggest one is gravity. Right now there's a pen up in the air here. Am I doing work right now? Nope, but I did work to get it here though, right? Because the pen was not here to begin with. The pen was, I had to lift it up, right? It now has the capacity to fall, right? Just due to gravity. So anything that has the ability to fall has gravitational potential energy. Elastic potential. We actually have a formula for this that we'll use later in the course. But I mean, any sort of bungee, any sort of stretchiness. Even a basketball, believe it or not, has elastic potential energy. You guys know that? That's actually what causes it to bounce back up again. When a basketball hits the ground, it doesn't just hit the ground like this and then just bounce back up again. The basketball will slightly, I'm second drawing, give me a sec. I'll do a better job. Basketball, rather than doing this, will slightly, I'm really exaggerating, but it'll slightly deform a little bit. It'll compress as it hits the ground. And then as it springs back, that's what causes it to actually bounce back up. Does that make sense? Yeah. If you ever see like a slow motion video of something like that, it will actually have a little bit of springiness to it. That's what gives it the ability to bounce back. There's also chemical potential. So I mean, huge overlap here with what you guys who took chemistry from me before. We had a whole unit on this sort of stuff, right? If bonds release more energy, then it's exothermic. We'll talk about nuclear potential energy. So that's how atomic weapons have been developed. If you can find a way to either do you guys know the two types of nuclear possibilities? Okay, we'll do this in the future, but they're known as fission and fusion. Anyone ever heard those words? Fission basically means you take the nucleus of an atom and you break it into pieces. And that's incredibly difficult to do, because if you guys remember anything about chemistry, really we're not supposed to be able to change the inner nucleus. We can change the electrons, that's easy to do. But if you can actually break apart that nucleus, that's a nuclear bomb or nuclear energy. So if you can break it apart, it's fission. And if you can actually take two nucleuses and put them together, that's known as fusion. That's what our sun does, actually. Our sun takes a hydrogen atom, adds another hydrogen atom, and it turns it into helium, essentially. And so at a nuclear level, there's a lot of potential if you can actually bust up that nucleus or put them together. We're going to talk about this in grade 12. This is actually one of our last units. For right now, we're just going to focus on the gravitational potential energy, though. So, you've probably heard of gravity at some point. Right? Gravity causes things to fall. That's only based on our perspective, though. Because of the fact that we're on Earth and we're on the ground, we kind of recognize that gravity kind of pulls things down. But that's not exactly true. For example, let's see if I can try to illustrate this well. Imagine this is the Earth, right? And we are standing right here. If I were to drop something, it would go that way, right? But if I try to keep that exact same frame, someone on the other side of the planet in Australia right now, if they were to drop something, their perspective is also that it's falling down from them. But I mean, really everything gravity-wise, it's more like it goes in. That might be a better explanation. Does that make sense? Right? Gravity is really pulling everything to the center of the Earth, in a way. Does that make sense? So I don't know that down is actually the right word for us to use for gravity. Basically, any two masses are attracted towards each other. Why do we notice it? Well, we only notice it if one of the masses is really large. Technically, there's a gravitational attraction between me and this table. You guys ever heard this before? I told you guys this in grade 10 last year, I think, right? Any two objects that have mass actually have a gravitational force between them. But there's really only, it doesn't do anything unless something is either really, really large or possibly really close, but like we're talking nanometers close. So me and the table have a gravitational force of attraction, but do the two of us move towards each other? No, it's so small it wouldn't matter, right? But if one of the objects is the Earth, then yeah, things will get attracted to it. Why do people who walk on the moon then kind of bounce a little bit? Is there gravity on the moon? But smaller amount because the moon is a smaller object. Does that make sense? All right. So I mean, it doesn't matter how good your jumping skills are. You can dunk a basketball on the moon because you're going to bounce too high. In fact, sometimes there's a danger for spacecrafts that if a spacecraft is trying to land on the moon and they accidentally bounce too high, they might actually bounce right out of the moon's gravity orbit, and you might actually, does that make sense? You might actually lose your space rover or something like that. So you have to be careful because gravity is a lot smaller there. Conversely, if we were to ever land a person on Jupiter or Saturn, they probably would never survive because gravity would be so strong there. They would get, like if this is the planet, my hands there. This is the planet, right? If you were a person, you would be getting so sucked into the center of the planet, it would compress you. Like you would get squished in. Does that make sense? People who spend a lot of time in outer space, actually, they get muscle and bone issues because there's nothing kind of forcing them down to Earth, right? As I'm standing here, all of my internal organs, all of my biological structure is getting pulled down towards the Earth. If I go into outer space, there's no gravity kind of keeping it all in place, and so it kind of floats a little bit looser than it's supposed to be. That's probably maybe good if you've got, I don't know, arthritis or bad knees, but over time it actually causes muscle weakenings because they're not working in the same way they normally work. Does that make sense? I can get back on. Let's get back to this. Okay, have you guys heard this number before? Gravity's acceleration is 981. Hopefully you've heard that value before. So let's do an example.
Are we going to need to know that?
Yeah, I think it's probably even on the other side of your formula sheet, probably, the acceleration due to gravity. Okay, so here's our first formula. It's actually not quite to energy yet, it's actually about weight. I should talk about the terms weight and mass, because these are not the same as each other. We often use them interchangeably, but from a physics point of view, there's a big difference. My mass is what I measure when I stand on a scale. That is how heavy I am. Weight, technically, is how much force that mass applies due to gravity. So when I say that I'm going to go weigh myself on the scale, that's actually, we can use that word, but what we're doing is we're massing ourselves on the scale. We're finding out how much mass we have. A weight is actually how much the force of gravity acts on the object. So obviously, though, the bigger something is, the more that force happens to be, right? If I were to drop this pen on my foot, wouldn't be too bad, because the mass of this thing isn't really that much. If I were to drop a bowling ball on my foot, it's going to hurt, right? Because the force is going to be more. Why is the force going to be more? Because the mass is more. Does that make sense? So anyways, try to use those words properly. Weight is actually how much force gravity applies to a mass. Okay, here's the formula for energy then. The amount of gravitational potential energy you have is then the amount of mass you have times by gravity, which is kind of what the last formula was. But we got to throw one more thing in there. Height. If I were to drop a bowling ball on my foot from this high above it, it's not going to feel good, but it's not actually that bad, right? If I were to drop a bowling ball on my foot from a big distance, you guys can intuitively guess, right? That's going to have even more energy transfer. More work is going to have been done. So 3 variables. You need to know how heavy something is in kilograms. But that's a mass, not a weight. You need to know how fast it's going to accelerate due to gravity and how high it goes. So let's do it.
What does that little G mean?
Sorry, this G right here?
Yeah.
Yeah, okay, good question, thank you. Sometimes because there's so many forms of energy, we might call this the gravitational energy. We might call this the energy due to a spring. This would be the energy due to chemicals. This would be the energy kinetic. Does that make sense? So that little subscript is just there to help us know what type of energy we're going to work with. Good question. Oh. Okay, you used 565 joules of energy to move a 12 kilogram box up the stairs. How big are the stairs? So tell me what we know. We know how much energy we used. 565 joules. This number right here is a mass, not a weight, a mass. What are we looking for? A height. Yeah, we need to know what like our change in height was. There's actually one piece of information then that's kind of implied. Gravity. Right? Gravity is always 9.81 meters per second squared. Yeah, basically just throw them right in the formula, right? Your energy due to gravity will be equal to your mass times gravity times however high you go. I'm going to write the 656 joules as Newton meters again, though, just because it makes the units work sometimes nicely. Actually, I'm going to do more than just that. That's going to be a Newton meter. Do you guys know what a Newton's units are? Write this down somewhere here, because it may help you once in a while. A Newton is equal to a kilogram times by a meter per second squared. That's what a Newton is equal to. Just off to the side. Maybe even throw it on your formula sheet. Because if you can get really good at you doing unit canceling, sometimes it can save you if you're really stumped on a problem. You can just look at how the units work. So what I'm going to do here then, if it's okay with you guys, rather than writing that as 565 joules, or even writing it as 565 Newton meters, I'm going to write it as 565 kilogram meters per second squared. That's what a Newton is actually equivalent to, times by a meter. I lose you on that one?
Yeah, why would you just do it in meters?
Because we'll see how this cancels in a second here. The mass is 12 kilograms. Gravity is 981 meters per second squared, and I'm really running out of room here, so imagine that's right next to it there. That's your height. Okay, watch the units. If I divide by 12 kilograms and the 9.81 meters per second squared, maybe you can see why I chose to break that up into smaller units. If I divide by the 12 kilograms and the 9.81 meters per second squared, watch the units. I'll just give you a second to catch up first.
Where did that other meters come from on the left side?
This was a joule.
Yeah.
A joule is a Newton meter. So this bit right here is the Newton part of the Newton meter. Mm-hmm. That's the meter part of the Newton meter. It's the extra meter. Yeah. I may need to go over that again a little bit later. Check out the unit canceling though here. Kilograms cancels. Okay, one of these meters can cancel. Why don't I just choose that one there? The per seconds is on the bottom of a fraction. The second squared is on the bottom of a fraction, right? This other second squared, also on the bottom of a fraction. What unit was left? Yeah, just meters. Isn't that kind of what we want, right? Like we're trying to solve for a height. Height should be measured in meters. So although it's okay if you were to have just written this in joules or in Newton meters, it doesn't hurt. In fact, I really encourage, know what units, how units work. So maybe I should give you a couple of equivalencies. Okay. A joule is equal to a Newton meter. And a Newton is equal to a kilogram times by a meter per second squared. Okay, so those are just a couple of equivalencies that wouldn't be bad to have written down somewhere. Even if you don't do your units in that sort of way, what really matters now is can you handle the math? And I'm going to pull up the calculator here just to make sure that everybody does this properly. I'm sure most of you know what to do properly here, but here's what you don't do. Don't type in this. If you type in 565 divided by 12 times 9.81, that's not going to work. Why? Yeah, the way your calculator does order of operations, it thinks that it wants you to do 565 divided by 12. But then it thinks that the 981 is on the top of the fraction, but it's not, right? We want that 981 to be on the bottom of the fraction here. So don't do this. That's a very incorrect answer. So here's your two most likely options. Go 565 divided by, and then use a bracket, 12 times 981. That'll work. Or the other option is do 565 and think of it as, well, you have to divide by 12 because you had to divide the 12 off this side, right? But you also have to divide off the 981. Both of these pieces have to get divided away. And just think of it as doing it like individually. Okay. So the stairs was 4.8 meters. That makes sense? Okay. Time to do tell again. I think we're doing good. Okay, let's talk kinetic energy then. So kinetic energy then is usually what happens once the potential energy is changed, right? Once we've used our potential energy to do something, it causes something to be in motion. And so that's kinetic energy. It's the energy of somebody moving. I pulled the slingshot back. So I did work to pull the slingshot back. It has potential energy, right? As I let go of the slingshot, that potential energy is going to turn into kinetic energy as the thing moves. That makes sense. So it just depends then on how fast it's moving, and again, how heavy it is. That's the kinetic energy formula. So here's a good time to talk about that little subscript then. If put a little K in the corner, that's just to indicate that we're going to do kinetic energy rather than some other type of energy. So this formula is 1/2 of mass velocity squared. For you guys in grade 12, is this ringing any bells? I know it's been like 2 years. A little bit? You guys in grade 11, we did this last year. Are you familiar with it? Okay. If I lose some of you guys, because I'm kind of going through this at a faster pace than normal, talk to me later. So, but I mean, essentially the same thing still applies, right? Once you know how to use your formula, it sure helps if you know how to do your units though, right? So if it helps, just for canceling it first, remember a joule is really a Newton meter. But a Newton is a kilogram meter per second squared, still times by the other meter. So if that helps when you're trying to look at your units. I know it's ugly. Get used to it, I guess, because most of the units that we work with are composites. Right? Like the base units are things like kilograms, meters, things like that. Most of the other types of units that we'll use, like watts, joules, newtons, gravitational field strength, when we get to some of those crazy ones, most of them are actually composites of things. And so you'll eventually have to memorize that capital B really means a Tesla times by a meter divided by a candela, or whatever it happens to be. So I'm just making stuff up right now. Okay, let's do an example. Tesla is also a measure of gravitational field, but it's also the car brand. Okay, car weighs 1,500 kilograms. It moves 14 meters per second. Let's find its kinetic energy. So we know the mass, 1,500 kilograms. I gotta be honest, you probably could skip this step if you wanted, but I would still encourage that it's not necessarily bad to build healthy habits, because not all of the formulas we work with are going to be super duper easy that you'll just be like, oh, look, there it is. So it's not a bad idea to write down what you know. We want to find our kinetic energy. Does mass have a direction? No, there's no way mass could ever have a direction, could it? It's a scalar. Could a velocity have a direction? Yeah, I mean, I said speed here, but could it be a velocity? Like, if I gave you a direction to it, could we attach one? Yeah, you could. But energy is going to be vectorless. Okay, we don't count that. And here's the reason why. When we throw our formula together, we're going to do mass, 1,500 kilograms. That would never have a direction, right? We're then going to times by the speed, or velocity if we attach a direction to it. But we're going to square that number. So even if this thing had a direction, whenever you multiply two vectors together, we always turns into a scalar, actually. That makes sense? So even though we possibly could have said that he was going east, even though we could have given you a direction there, it wouldn't matter. Math rules, and this is way beyond what we'll even cover in this course, but if you ever have two things that are vectors, a vector times a vector is a scalar. So don't worry at this point here about whether there's a direction to it. It really doesn't matter. 1,500 times 14 times 14. I got 294,000. What are units be? Did you guys get something different than me? Thank you. Good catch. Okay, so if I divide that by half, 147. Okay, thanks. Good catch, guys. Okay. The units for this then would be kilograms. From this kilograms here, right? I'm just going to kind of rearrange where they go. You see how you've got a meters right here? Per second. But there's also another per second. I'm going to take this meter, that second, and that second. I'm making a meter per second squared. And then I'm just going to throw an extra meter sitting on the end. So this one, and that one give you meters per second squared. And this meter gives you the extra one. This is known as a Newton. And a Newton meter is known as a joule. So our unit can go to joules. Once you get the hang of it, you'll just go right there, okay? But I think this is good practice. Okay, here's one option. We could call it 147 kilojoules. Because like 3 zeros is a kilo of something. But I don't think that works for sig digs, though, does it? Because I only get 2. So probably the best option is to go 1.5 times 10 to the 5 joules. That's probably the best option. If there was a prefix that went to the power of 5, like a giga or a kilo or a mega or something like that, I guess we could change that, but we don't actually have one for the power of 5. So that's probably the best we can do. I guess you could call it, no, that's probably the best option. What? Questions on that? Stamkos is shooting a hockey puck. Why is the puck getting so much energy? What happens in a stick? Flexes, right? That's your elastic energy in a way, right? That's what's happening is at this point right here, before he releases the puck, he's done work. He's applied a force over a distance to a stick, right? And he's given it that flex, that there's potential energy just waiting right there. And as soon as the friction between the stick and the ice gives way, the stick is going to bend, right? And basically think of it like a big catapult, right? What's going to happen is it's going to fling the puck towards the net, right? Physics and hockey. Okay, anyways, let's give this a try here. So we've got our kilogram hockey puck, our kinetic energy. Let's find out how fast you can shoot the thing. So, mass, 0.21 kilograms. It's already in kilograms. Big note here. We will often measure things in grams. The base unit, though, has to be kilograms. Okay. So if we ever measure something in grams, we got to put it into kilograms. We have our kinetic energy, 73 joules. We don't know our speed or velocity. If I don't write a little arrow hat over top of it, because of the fact that we're going to square it and turn it into a scalar, it's not really the end of the world. If that makes sense. So because we're going into energy anyways, that doesn't really make a difference. Okay, so kinetic energy is 1/2 of mv squared. Let's not screw up this time, Chris. Okay, I'm going to do it a different way here. Rather than converting units, I'll just go with joules. If this is okay with you and you feel comfortable, don't worry about converting a joule every single time. It'd be good to know how to if you need to, but I'm not going to require you to. How do you get V by itself? Here's what I did. This 1/2 right here, I times by 2. So to get rid of this guy, I'll times by 2. That gets rid of a 1/2. To get rid of the 0.21, divide by 0.21. And then to get rid of the fact that it's velocity squared. So in your calculator, at some point, you need to do the square root of 2 times 73 over 0.21. That'll give you your velocity. I got 26. You get the 2? Okay. For my purposes, I'm cool if this is what you do for work, something along these lines. I mean, whatever shows something. But I would like to talk real quick again just about the units hidden inside here, just so you kind of get how that worked. We had a joule, and we divided by a kilogram. A joule is equal to a Newton meter, and a Newton is equal to a kilogram meter per second squared times by the extra meter that was still sitting there, divided by kilograms. That's how our units worked. So right off the bat, you guys can see how the kilograms canceled, right? Well, the units I would have been left with then would have been 2 meters and a second squared. So I mean, meters squared and second squared, right? But don't forget, we still square rooted the whole thing, right? So when we square root the whole thing, essentially what you have, if I can go down here, is you had a meters that was squared, you had a seconds that was squared, but you square rooted it all, right? Well, so then the square signs go away and you get meters per second. That's not necessary to solving the question, but again, that'll help, especially as we get into more challenging types of formulas. Okay, so then this is kind of just a little bit of a recap here, just what I've got left. Yeah, last slide here. So work essentially changes energy, right? Work is changing energy. Work will either add or remove kinetic energy. Think of the flexing hockey stick. The work that Michael would do to flex his hockey stick and take a slap shot of a hockey puck, right? That work will give more kinetic energy to the hockey puck. That makes sense. But I mean, work can even go in the negative direction, right? Let's say a pitcher throws a ball. He's giving the ball the energy it needs, right? Why does it stop though? Well, the catcher does work in stopping the ball. Does that make sense? He is going to do some work to cause the ball to slow down, essentially, right? It's going to change its kinetic energy from going really fast to nothing, right? So it is actually possible, I guess this is what I'm getting at here, you can do negative work. Sounds weird, but if I asked you to do negative work in class, how do you do negative work, right? That'd be like really goofing off in class, right? But in the physics perspective, negative work is where you do a force in the opposite direction of the ball's motion, right? So if my force is going this way, right, but the motion is going this way, imagine that there's a train coming towards me, is a bad example. And I try to push on the train this way, and I'm Superman, so I won't die, right? I am doing negative work, right? Because I'm going to slow it down, right? So if the train is going this way, and I push it this way, that'll make it go faster. I'll be doing positive work. If the train is going this way, and I push the other way, and I'm trying to slow it down, then that's negative work. Okay? So it is possible to do negative work. This is what I'm trying to say. Okay, we managed to get it all done in a really good amount of time because you guys are done in just a few minutes here, I think, right? So let's just do a quick recap. I need you to know a couple new formulas. The 4 main ones are that work is energy. If I ever give you a work value, it's an energy value. Same thing. I need you guys to know the formula, as rare as it is that we use it, the formula for weight. Weight is not how heavy you are. Weight is how heavy you are times by gravity. Okay? So mass times gravity is actually what weight is. You should then know the other 2 formulas. Mass times gravity times height is how much potential energy you have due to gravity. And 1/2 mv squared is how much energy you have that's kinetic. It sure would help to know the units and how they work, because really all of the units that we do in physics. Give me a second. I'm going to go back to one of the very first slides we did. It's a long ways back. These are the only units we use in physics. Meters, kilograms, Kelvin, seconds, moles, amps, and candelas. Those are like the main ones. If I ever talk about a joule or a watt or whatever it happens to be, they're composites. So like what did we just say, a Newton? A Newton was a kilogram meter per second squared. Does that make sense? So it wouldn't hurt to have them written down on your formula sheet or memorized. I'll let you guys use the formula sheets, by the way, with whatever you write on them. So it doesn't hurt to throw it in the corner somewhere. I think those are kind of the main highlights for the day. So, any questions? Okay, last spot, and then you guys can, I guess you may as well not take off because we got class still, but we'll pack up here. Monday, we're going to do a quiz. Okay. It's not meant to be anything other than, let's just see where you're at.